All right, the call stack. Now, before I even jump into this, this is going to be like very idealized talk. It's going to be not necessarily exactly how every computer, every programming language is going to work, but it's going to give you the idea of something important. The call stack. So we're going to learn about the call stack. We're going to learn what a call frame is. Long story short, who's seen stuff like this in the Visual Studio? This is the call stack, and it says right there, call stack. The issue we were having today is we were looking at the call hierarchy, which was a different thing. This is the call stack. And what it's telling you is basically where in the program you are. If we go to the bottom of the stack, oh, before I continue, this is a stack. It's a stack in the same sense of the stacks that we were talking about before. It's a stack. The program starts at the main function. We push that function onto the stack. Look at what's at the bottom of the stack. Main. And then within main, it calls the function level order, whatever that is. And then level order calls level order again, which calls enqueue, which calls is empty. Basically, currently, my code is in the function that's at the top of the stack. And if the question becomes, well, where did I come from? Like, which function called me? I just go one below in the stack. And which called that? Go one below in the stack. That's the call stack. You may have been using this for debugging purposes already. If you have, awesome, good. But this is very important. So it's a stack, and it's used to store information needed for methods, functions, when the program's running. It's important. This is how a lot of the bookkeeping is going to take place for your program. It stores the local variables, formal parameters. That's like the parameters in your, like the function parameters. Return value, and the memory address of where to return. Because remember that code is in RAM somewhere, so when it returns, it needs to know where to return to. Basically, it knows where to go once it's done. The top of the stack is what's currently being run by the computer. At any given time, the thing on the top of the stack is where it's run, like where it is. The bottom of the stack is going to be our main. The function is called, when a new function is called a new call frame or activation record, depending on whatever, we create a new frame to keep track of, okay, I'm calling a new function. I need to create a new frame. That frame is going to hold on to the return value, which we don't know yet, local variables, the formal parameters, and where I'm going to return once I'm done. And I push that onto the stack, because it's a new function call. So the new function call gets that little bookkeeping thing called the call frame, and we put it onto the stack. And there, we've updated our bookkeeping, and we're in there running that code. A call frame is contains the information the current method needs in order to do its thing, like the local variables. The ones that are created and stored in memory within that function. The stuff that it needs to know. Those local variables, assuming they're in static memory, once that frame is done with, once that function's done, and like we're done, we need to go back to where the function was called, and when it gets thrown off the top of the stack, those local variables are destroyed by C++. It's fine. That's the memory management C++ is doing for us, because it's in static space. If there's a pointer, then we might be in trouble. Like if we're storing one of the local variables is a pointer to something in dynamic memory, we might be in trouble. But that's just the rule as before. Stores the parameters, return value, and the memory address where to return. So if we have a look at this code, I have function 1, function 2, function 3, function 4. And then I have my main. And my main calls function 1. So I'm going to hit run. When I hit run, what's the first thing that should be pushed onto the stack?
Main.
Everybody yell the answer on the count of 3. 1, 2, 3.
Main.
Main. What does main call?
Function 1.
What is function? Okay, function 1 will print out starting function 1, calling function 2. Then what happens?
Function 2.
Boom. Starting function 2, calling function 4.
Function 3.
Who said 3? So we jump down to start. Okay, we start and then finish. Now function 4 finishes. What do you think is going to happen?
Function 3 will
Pop it off, because we're done. Return to the calling function, and now we are basically, in function 2, we're here. Then what should happen?
that should be return function 2.
We return to function 2, or function 1. So we're back here, so now we're at this line of code, and we go here. Calling function 3, then what?
Push function 3.
Function 3. Start, finish, then what?
Return, peak function.
Peek? No.
Pop.
Pop. There we go. So now we're here. Now what?
Pop function.
The quietness is concerning me. Is this because it's so easy, or is it because your mind's blown by the complexity of this?
Pop function.
Pop. Then what?
Pop main.
Pop. We're done. That's when we know we're done. We're good. Program's done. Any questions about that? The quietness, I'm not trying to be mean. Yeah.
Can you go over it again?
Yeah, let's do it. We call main. That's a function, gets added to the stack. Main calls what?
Function.
Function 1. We push it to the stack. Then what happens? I'm going to point to someone.
Calls function 2.
We push it on the stack. Then what happens? No, not you, you.
Me?
Yeah.
Calls function 4.
Boom. Perfect. Then what happens?
Pops function 4.
Then what happens?
I'm not sure.
Why not? I'm asking because you don't understand, or you stop paying attention.
I just spaced out, sorry.
Ah. Who wants to give it a go?
Push.
It's going to pop function 2 off.
No. Push function 3.
No, function 2.
Function 2 should.
Because we finished function 4. You missed where we were. So there we go. What happens? Not sure?
Function 3.
Pushes function 3.
What do you say?
Pushes function 3.
Perfect. Then what happens?
Pop function.
Oh, I gotta point to someone. Stop mumbling. What do you say?
Pops function 3.
What do you say?
Pops function 1.
Did you know, or was that just a damn good guess? You had a good feeling. You had a feeling. Then what happens? Everybody. Good job. Program finishes. We're good to go. Does that help? A little bit? Okay, what's your question?
Are we just going through it and then backwards?
So basically, I think I see what you mean. We call main. Main goes to that first line which calls function 1. We jump into function 1. We run the first line of code, the second line of code, then we call function 2. So okay, main, function 1. Go into function 2. Call the first line, second line, call function 4. So now we're in function 4 executing that code. Then function 4 runs, this line runs, then we get to here. There's nothing left. So the function is now done. And we return to where we were before, which is in function 2, that line that says call function 4. We immediately then print out finish function 2. And now that we finished function 2, where do we go? We'll go back to function 1. And then we're now on that 1, 2, 3, 4th line that says calling function 3. So it's like going up, like it's pushing, popping the stack. It's just the bookkeeping of what function we're in. So, yeah. Already showed you this call stack. When C++ pops things off the stack, it knows how to get rid of the things that were in the call frame. Like the local variables, ints, characters, floats, pointers. But the pointers, if they're pointing to something in the heap, that dynamic space, we might be in trouble. Because we might delete what they're pointing to. But the pointer variable itself will be deleted, because it's fine, but not what it's pointing to, if it's in the heap. So what's going to happen if I call this function? You have a question?
About the other thing, like, the pointers, like, we wouldn't really, like, if you were just deleting, like you should, you wouldn't run into a problem with that. Like, because
Yeah.
you're deleting it before it's over anyway.
Yeah. But remember, anything that's like those local variables, you don't have to say delete those things, because it knows how to delete those things. But if you were deleting that thing that I was pointing to, yeah, this isn't anything new. This is what we've been doing since the beginning of the semester. Good question. What happens if I run this function?
Keeps calling itself.
Just take a second, look at this code, make it make sense. Remember, the tip here is there is no trick. This isn't a trick. What are the rules? Follow the rules. There's nothing, this isn't new. Just follow the rules we just talked about. The stack, call my main, and I call uh-oh. So uh-oh, okay, I call uh-oh. And then what does uh-oh call? Who calls what? Who calls what? Who calls what? Who calls what? What?
Uh-oh.
Oh, it's overflow.
Who knows what this is called? Say it louder.
Stack Overflow.
Stack Overflow. Interesting. Who here has heard that word before? Huh. Where have you seen that? Did you have a comment or you just had the answer?
Yeah, I was just going to say Stack Overflow.
Stack Overflow. This. So what happened? Explain this to me. What happened? What's going on? I want somebody different. What do you say?
Every time we call the function, and inside the function, it calls itself, and it keeps calling itself repeatedly without ending the
Bingo.
function.
So we just kept pushing things on the stack. I mean, if we kept doing this, the computer's going to be in big trouble, right? Because it just keeps going like, oh, I need to allocate more memory to hold on to this point. Oh, now that's more memory. Oh, more memory. And it's just going to go. Fortunately, the computer is smart enough, like C++ is smart enough to go like, whoa, 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 whoa. We got a problem. Stack Overflow. Clearly, we're in a runaway situation. Who knows what we call this phenomenon? Not the Stack Overflow.
Recursion?
Recursion. We've got recursion going on here, but there's no like bottom. This is kind of like looking into, like if you stand in between mirrors. It just goes on forever, right? It's crazy. You had a question?
Is it gonna keep printing out like we?
Yeah, it'll go wee until it goes like exception. But yes, it will print out wee. If you don't believe me that this is going to happen, type this into Visual Studio and watch what happens. Any questions, comments, concerns about this? No? Now, clearly this is like an infinite loop, right? But it's not like a for loop, it's not a while loop, it's different. It's recursion. Now, for those of you that came from engineering, did you learn recursion? Yeah? Okay, cool. So, no? No? All right, well, you're going to have a lot of fun now. Recursion is amazing. Now, I know I used this example last semester, but I'm going to do it again. Recursion can be very helpful. If done right, it is helpful. It's amazing. It's great. But if you make little mistakes like something like this, you're obviously going to run into trouble. Most things, like most mathematical things, are kind of like recursive. Sorry, I worded that really poorly. A lot of like the mathematical, computer sciencey stuff ends up being like recursion is really important. So I'm going to ask a question. I need a volunteer from the last row. Someone put up your hand. All right, you. I got a question for you. But let's pretend you are remarkably naive and you have really bad vision or something. All you can see is the one row in front of you. Okay? That's all you can see. That's it. Exactly. Good. So I know last semester I used this example, but I'm going to use it again. I have a question for you. How many rows are there in this classroom? as far as you know, there's you.
Okay, so 2.
There's at least 2, I guess, right? But here's the thing. You know that there's at least 1 where you are. So here's what you're going to do. If you knew how many rows existed in front of you in total, because you're aware that there's probably some in front of you, but you just can't see them. If you knew that there were some in front of you, and you knew how many were in front of you, how many would there be in total, knowing that you're at the end? How many would there be in total if it included you? Let's say there were n rows in front of you. How many would there be in total, including you?
N plus 1.
N plus 1. Exactly. So that's the answer to the question. This might seem silly, but the answer to the question is the total number of rows there are to you is the total number of rows there are in front of me plus 1. That's it. That's it. If you don't believe me, we're going to see how this works. But this core, simple, basic idea is remarkable. It's simple. How many rows are there in front of me? Well, how many rows are there in total is how many rows are in front of me plus 1. That's it. That's all I need to know. Now, what's your question?
So what was the only could see the first row in front of
So here we go. Here's what you're going to do. Because you don't know how many rows there are in front of you, right? You don't know. But you can ask the row in front of you, how many rows are there? So ask him how many rows there are.
How many rows?
So here's the thing. You don't know. But you know that there are some number of rows in front of you. And if you knew how many rows were in front of you, you just add 1. And then you can tell him what you found out. So the answer to your question is simple. It's literally the exact same question before. Our answer is before. It's how many ever rows there are in front of you plus 1. So you just need to know how many rows there are in front of you. But here's the thing. That's not your problem. You know whose problem that's going to be? His. Ask him how many rows there are.
How many rows in front of you?
You don't know. It's the number of rows in front of you plus 1 to include yourself that you can tell him. But you don't know the answer. Now, ask him how many rows there are.
How many rows are there?
Ask him.
How many rows is that?
Now, here's the thing. You know that there are no rows up here. You happen to know, because he's looking ahead and there's nothing more. And if there's nothing more, how many rows must that mean there are in total, including you? 0 plus 1. It's 1. So how many rows are there? You know it's 1. So you better tell him.
1,
So how many does that mean there is with you?
2,
3, 4, 5, 6.
1, 2, 3, 4, 5, 6. How about that? We answered the question recursively. You didn't know the answer to the question was, how many rows are there in total? Well, it's 1 plus how many rows are in front of me. But that wasn't your problem to find out. It was his. Recursion's amazing. Who here knows? Who here has seen this before?
Factor.
At the back, you've seen that? Yeah, okay, so here's the thing. You know recursion whether you like it or not. What does this mean?
Product of all the integers till then.
If I said 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1, although that's kind of whatever. Right? So, let's define this recursively. N factorial equals either n times what?
N minus 1 factorial.
N minus 1 factorial if n is greater than 1, I guess. But if n's 1, we just return 1. That's it. There. That's recursion. That's a recursively defined thing. So let's follow this rule. I want 5 factorial. So is 5 greater than 1? Okay, so 5 factorial equals 5 times, what's 5 minus 1?
4.
Oh, 4. 4 factorial. Do I know the answer to 4 factorial?
No.
No. But I know that the answer to 5 factorial is just 5 times 4 factorial. It's easy, that's it. It's 5 times 4 factorial. And now you're saying, yeah, but you don't know what 4 factorial is, and you're right. But is that my problem? No. Someone else's problem. I'm going to ask someone else to figure that out. So 4 factorial equals what? Well, is 4 greater than n?
Yes.
Yeah. So it's going to be 4 times
3 factorial.
3 factorial. I don't know why I put it in brackets. Great. So 4 factorial is just 4 times 3 factorial. I'm done. But of course, what's the problem?
What is 3 factorial?
What's 3 factorial? Okay. So 3 factorial equals what? Well, is 3 greater than 1?
Yes.
Yeah. So
3 times
3 times 2 factorial. Great, I'm done. Except,
2 factorial.
I don't know what 2 factorial is. So
2 factorial.
2 factorial equals what? Well, is 2 greater than 1?
Yes. 2 times.
So it's 2 times 1 factorial. We're running out of room. So I'm done. It's 2 times 1 factorial. All right, well, I need to know what 1 factorial is. 1 factorial, well, is 1 greater than 1?
No.
So that means 1 factorial is what?
1.
How did we know that? Because it said it right there. By definition, 1 factorial is 1. So, if I now know 1 factorial is 1, well, I'm in great shape. I can now answer the previous question. 1 factorial is 1, which means I can replace this with 1. What's 2 times 1?
2.
Which means I can replace 2 factorial with what?
2.
What's 3 times 2?
6.
6. So 3 factorial is equal to 6. Which means I can replace 3 factorial with what?
6.
What's 6 times 4?
24.
So 4 factorial is 24. Now that I know the answer to that question, I can answer this one because I know 4 factorial is 24. What's 24 times 5?
120.
120. I had to go down and then back up. Any questions about that?
I had a question about the Stack Overflow itself.
Yeah.
Does it have to be infinite to cause a Stack Overflow?
No, it doesn't. It could just be arbitrarily large and you could trigger it.
Okay.
But you might think, well, what if I wanted that? Well, tough.
That's something like 900 calls or something.
I don't know what it is. It's going to be a lot. I think it's in that. I think it depends on a couple of things. But I remember in Python we added counting infinitely, and it would stop at 900 and something. I think that's what you're remembering, right?
Yeah.
Yeah. Other questions? Okay. So the point of the lecture, what is recursion? See examples, see where it's awesome, some pitfalls, whatever. This is the example I already showed you. How many rows are there in here? Well, that's too hard to count. Let's figure it out another way, recursively. Okay. So, recursion. We define something in terms of itself. Use the word or concept being defined in the definition of itself. That's what I mean. It's kind of weird. But a recursive definition is a recursive definition, I guess, is true in that case. But includes a base case, too, that defines something clearly without reference to itself. Base cases are important. And it's the lack of base case that was the problem with that Stack Overflow. It didn't stop. There was no bottom. We just kept going deeper and deeper and deeper and deeper. There was no end. That would run to infinity. It's weird, right? So we need this base case, we need a recursive definition. So, a group of people. We can define this iteratively. This is a weird concept, but we can define a group of people iteratively. A group of people is 2 people. Would you agree that if we had 2 people, we could say that's a group of people? Perfect. Let's define that. 2 people, that counts as a group of people. Or 3 people. 3 people is also a group of people, right? 4 people is also a group of people. 5 people, 6 people, 7 people, 8 people, 9. What I can keep going on forever, right? These are all going to be groups of people. Now, if I wanted to write out all those things, I'm going to be in trouble. Like, I'm going to have to write that out infinitely. So we can define this recursively. Let's define a group of people recursively. A group of people is 2 people. So by definition, if you have 2 people, it's a group of people. Otherwise, a group of people is a group of people plus 1 more person. Raise your hand if you like that. Raise your hand if you don't like that. Let's make sure it makes sense. Because it does. We're not going to do anything crazy. We're just going to follow the rules. Most of the time when you start getting worried about these rules, it's because you're thinking too much. Fall back on the basic principles that we've learned. If I have 2 people, it's a group of people, right? So I have a group of people, which is 2 people. I have 1 more person to it. That's a group of people plus 1 person. Which is therefore, that means 3 is what? Which would then therefore mean that 4 must be a group of people. And then 5 must be a group of people. And 6 must be a group of people, right? Now that was very constructive. I started at 2 and went up. But what if I ask the question, but is 10 people a group of people? Well, you don't know. You don't know yet. I know we kind of know, obviously, because we can count. But we don't know. Because in order to know if 10 is a group of people, if I take 1 out of 10, I have 1 plus 9. So I need to know, is 9 a group of people? I can't answer the question, is 10 a group of people, until I know if 9 is a group of people. Which I can't answer until what?
8 is
If 8's, then what?
7.
7, 6, 5, 4, 3. I don't know if 10's a group of people because I don't know if 3's a group of people or 4's a group of people, and so on. Then I go, okay, is 2 a group of people? Yes, how do we know?
Because 3 is.
But, because it says right there, it's in the definition. Oh, okay, so if 2 is a group of people, that means 3 is a group of people, which means 4 is a group of people, to 10. That was kind of like down and then back up. Kind of neat, right? You don't think so? Oh, I don't know what else to tell you. This is exciting. Base case, not base case. See how this one definition had the definition of itself in itself? Kind of weird, right? By the way, it's once things start to reference themselves where computer science gets weird. Or, let me reword that. It's where computer science gets fun. You may remember from last semester that statement, this statement is false. Right? This statement is false. Okay, what's so special about that? Well, so the statement's clearly talking about itself, right? There's like some self-referential thing going on. So I'm going to read the statement and assume that, why would I believe that it's lying to me? Right? So if I read that statement, I assume it's true. And if it's true, it must therefore mean what?
Statement is false.
That is
Is false.
false. But whoa, wait a minute. If it's true, it's telling me that it's false.
Right.
But if it's false, that must therefore, if the statement, this statement is false, is not true, it's false, what must that therefore mean?
Statement is true. It
That
is,
it's true.
it is not false.
So, if it's true, it tells me that it's false, which tells me that it's true, which tells me that it's false, which tells me that it's true, which tells me that... Do we see a problem here? How is that statement valid? What do we call this? A paradox. Right, yeah. What was that other example? Who remembers that other example I gave last semester?
Pinocchio nose is going to grow.
Pinocchio, that is one of the other ones. Pinocchio says, my nose is going to grow now. But Pinocchio's nose only grows when he's lying. So if he says that his nose is going to grow and he's telling the truth, it won't grow. But that meant he was lying, which meant it should have grown. But if it grows, that means he's telling the truth. Pinocchio better not utter those words, lest he become a black hole and devour the universe. Because as that system is defined, Pinocchio's existence, and the nose growing thing, he's going to be in big trouble if he says that. And we might all be in similarly bad situation. What was the other paradox we talked about? You don't have to know its name, but what was the examples I used? Come on, someone's got to remember.
Was it like the word heterological?
Heterological and autological. Words that describe themselves and words that don't describe themselves. So we have words that we'll call autological. Autological are words that describe themselves. Like, let's say short. Short's kind of a short word, right? The other example is pentasyllabic. Pentasyllabic. 5 syllables. The word like described itself. Right? That's an autological word. And a heterological word is a word that does not describe itself. Like, I don't know. I guess word. Why can I only think of autological words now? Someone give me an example.
Big.
Big. You're right. That definitely doesn't describe itself, because big's kind of small. So big is heterological. It doesn't describe itself. Laptop. Well, I mean, the word doesn't really, I mean, it describes a noun, but a laptop doesn't describe the word, right? Whatever. Pardon?
I think nouns are autological.
You think nouns are autological? But it's about the word describing the word itself. Okay, let's ignore nouns. Run. Run doesn't describe the word run, right? That doesn't make sense. But here's the thing. Is the word, so the first question I want to ask you is the word autological autological? Does the word autological describe itself? Huh. Let's ask a more interesting question. Everyone, hold on to your heads because they might explode. Is the word heterological, where do we put it? Is heterological autological or heterological?
Autological.
Hold on. My head's about to explode. If heterological is heterological, right? If heterological does not describe itself, but heterological means does not describe itself, which would therefore mean that the word not describing itself is describing itself. What? What the heck? Okay, clearly that's not the rabbit hole to go down. What about if heterological was heterological? Heterological does not describe itself. Okay, so if heterological does not describe, but if heterological does not describe itself, then it's not describing, which means it would be autological.
Yes.
We got a big problem here. These are paradoxes. 1,000,000 bonus points for someone who can name that paradox.
Liar paradox?
No, that's the first. That's not that one. Ah, no one gets the bonus points. All right. Anyways, I'll see you maybe later.